Physics is an experimental science in which experiments and observation of phenomena in nature are carried out to find the principles that relate these phenomena. Observations and careful experimentation and measurements are one side of the scientific process. The other side is the invention or creation of theories to explain the principles or laws that govern nature. Science requires testing of its ideas or theories to see if their predictions are borne out by experiment. It should not be assumed that a theory is proved by testing. First of all, no measuring instrument is perfect, so exact confirmation cannot be possible. Furthermore, it is impossible to test a theory in every single possible circumstances. Hence, a theory cannot be absolutely verified. Indeed, the history of science tells us that long-held theories can be replaced by new ones. To make judgments of what is relevant in observation and experiments, the leap of imagination is required. Because scientists can never include everything in a description of what they observe. Let's consider the example how two great minds, Aristotle and Galileo, interpreted motion along a horizontal surface. Aristotle noted that objects given an initial push along a horizontal surface always slow down and stop. Consequently, Aristotle stated that the natural state of an object is to be at rest. Almost 2,000 years later, in his re-examination of horizontal motion, Galileo chose rather to study the idealized case of motion free from resistance. Galileo imagined that if friction could be eliminated, an object given an initial push along horizontal surface would continue to move indefinitely without stopping. He concluded that for an object to be in motion was just as natural as for it to be at rest. Galileo found our modern view of motion by a leap of imagination conceptually without actually eliminating friction. Physical model and mathematical model. As we talk about model here, we don't mean a person who displays articles of clothing. In reality, physical systems are too complicated to analyze in full detail. So, we need a model as a simplified version of a physical system. On the other hand, lots of physical phenomena are invisible by our naked eyes. In order to understand a particular set of phenomena, we make use of model as a kind of analogy or mental image of the phenomena in terms of something we are familiar with. When we cannot see what exactly is happening, a model gives us an approximate mental or visual picture to hold on to. For example, light wave is a model to describe light by analogy to water wave. Since light has the same property of interference and diffraction as water do, which we are familiar with in our daily life. A theory is an explanation or possible solution that has been tested many times and still explains the observations. On the other hand, scientific laws are concise and general statements about how nature behaves. Sometimes, the statement takes the form of equation between quantities. Kepler's laws of planetary motion and Newton's law of gravity are two brilliant examples of how physics theories and laws were made. In 1609, Johannes Kepler published astronomical novel, a book containing 10 years of his efforts to understand the orbit of the planet Mars. He was using state-of-the-art astronomical observation from his mentor and employer Tycho Brahe. There were 3 models of the solar system out there at the time, but none of them worked very well for Mars. First, the Ptolemaic system put the Earth at the center with the Sun and planets orbiting it in perfect circles. Copernicus' heliocentric model set the Earth among the planets revolving around the Sun. Finally, Tycho Brahe put the Earth at the center with the Sun and Moon orbiting it, but let the other planet orbit the Sun. All 3 systems relied on circular orbits because the circle was accepted as an ideal shape. Copernicus, Tycho, and Galileo all believed that planets should travel along circular paths, but the data just didn't fit. Instead, Kepler found that another shape, the ellipse, works a lot better. In astronomical novel, Kepler states that Mars travels in an elliptical orbital around the Sun, which is one of the foci of the orbit. Later on, he explained his first law to include all of the planets and demonstrated that these shapes fit the available observations. The orbits of the planets in our solar system are not very eccentric at all. They are really very close to circular, which is partly why perfect round orbits seemed like a natural thing to expect in the first place. It wasn't easy to abandon a central idea like that, but with this first law of planetary motion, Kepler rejected circular orbits and showed that the ellipse could better explain the observed motion of Mars. Generalized to all planets, it states that the orbit of a planet follows an ellipse with the Sun at one focus. Thanks to meticulous astronomical observations of his colleague and employer Tycho Brahe, Johannes Kepler was able to test several rival hypotheses for how the Sun and the planets are arranged in the solar system, eventually leading to his three laws of planetary motion. Kepler's first law states simply that mass travels in an elliptical orbit with the Sun at one focus of the ellipse. His second law says that if you draw a line from the Sun to Mars and wait a fixed amount of time, that line will sweep out a certain area as Mars moves along its orbit. What Kepler noticed was that this area is exactly the same no matter where in the orbit you are. This is often phrased as Kepler's equal area in equal time law, and this law works because Mars doesn't move at a constant velocity. It speeds up the closer it gets to the Sun. So, if Mars is approaching the point in the orbit nearest to the Sun, it's traveling faster than if it is at the point that's faster away. In the first case, the line connecting Mars to the Sun is very short, but because the planet is moving faster, it covers a lot of distance. In the second case, the line segment is much longer, but Mars also moves more slower. Either way, the area swept out in a fixed amount of time is the same. Kepler and his contemporaries could see that Mars doesn't move at a constant rate, but they didn't know why. The inverse relationship that Kepler proposed between distance from the Sun and orbital velocity could explain the puzzling observation of Mars movements, but only if the orbit is an ellipse. A circular orbit would mean no change in distance from the Sun with time, and thus the velocity would be constant as well. These two statements, that Mars travels in an elliptical orbit and that its speed varies, so that the Mars-Sun line sweeps out equal area in equal time, were generalized to include all planets in 1621, and they constitute Kepler's first and second laws of planetary motion. The second law, it turns out, is also a consequence of observation of angular momentum, which was not a concept known to Kepler. In the 17th century, angular momentum is a measure of the amount of rotational motion in a body or system of bodies, like Mars and Sun. And in the absence of outside forces, it's a fixed quantity. This implies a trade-off between the distance at which Mars orbits and its velocity, like Kepler noticed. Just as a skater spins faster after pulling her arms close to her body, Mars has to move faster when it gets closer to the Sun. Kepler's statement that the area swept out by the Mars-Sun line is constant is equivalent to the statement that angular momentum is a constant as well. That is to say, that is conserved. The story that Newton found the law of gravity is super miraculous and interesting. University physics is full of stories and discoveries in creation, enhancing students' capabilities in creative thinking and innovation skills to confront the diverse challenges of the 21st century is an essential requirement for a college education. We are living in an ever-changing world where the quality of life are undergoing dynamic progression. Such a change has been possible and sustainable owing to the horizontal and vertical spreading of science and technology as the main driver for economic growth. In order to get a satisfactory grade for this course, you guys please be aware of the following. First, attend classes. Classroom participation is an important part in your grade. Second, write your homework and submit it to me in time. This is the only way to make your final exam easier. Thank you.